and we'll get rid of that, and we'll bring that up. Okay, so types of chemical reactions, all right? What we've done up to this point in this this last third of this chemistry unit is we've talked about chemical reactions. So we've talked about word equations where we have the reactants on the left and the products on the right. And we have, we can have chemical equations where we put the chemical formulas in place of the words. And then in the last day, we talked about balanced chemical equations where we have the coefficients, the big numbers in front of the formula so that the atoms are the same on both sides. Because that's the way chemical reactions work. They work in such a way that their atoms add up on both sides. So now we're ready to talk about different types of chemical reactions. There are many types of chemical reactions in our universe. We're only going to talk about 5 of them. And today I'm going to quickly go over 3 of them. They're pretty straightforward. In other grade 10 classes, they will be doing a lab on these 3 reactions, but it needs Bunsen burners, and I don't have access to Bunsen burners in this lab. Also, because I'm the chemistry guy, I have all kinds of different ways to demonstrate these different reactions. So instead of doing a lab, I'm going to show you these different types of reactions, and many of them involve lots of energy. They're high energy reactions, so we're going to have some explosions at some point in time. So it's kind of fun to see it sometimes instead of doing that. So let's first talk about our first type of chemical reaction. And you can see there, we're going to talk about combustion reactions. All right? As you're writing that down, I'm just going to get some pieces of equipment ready that I forgot to get ready. Combustion reactions, the reaction of a substance with oxygen gas. That is the key component to combustion, all right? Combustion is also commonly known as burning, right? So, oxygen must be a reactant. When we get going further on these different types of reactions, I'm going to show you different ways in which you can recognize which reaction type it is. And for a combustion reaction, it is the fact that oxygen is on the left as a reactant, that's going to result in you knowing that it's a combustion reaction. You need to leave that on the screen. You need to leave it flat, no, facing up, facing up. Put my PowerPoint on it because I know you can't see a thing, all right? And then you need to put it down, and then you need to look, okay, put it down. Okay, put it, good, that's good. There we go. All right, and then you can listen to me. Beautiful. Okay, now that we got things clear. So how are we going to know that it is a combustion reaction? How are we going to know that it's a combustion reaction? Justin? So where's the oxygen going to be in the chemical reaction? Okay, so where's it going to be in the chemical reaction? How do we know? Actually, I didn't get it stated because I got distracted. Where's it going to be? Zach, do you remember? Well, you're thinking of the explosion, but you see, I've got a chemical reaction right here down at the bottom. What side of the reaction will the oxygen be on every time we have a combustion reaction? On the left. Oxygen must be a reactant, okay? Sometimes we'll have oxygen as a product. That won't be a combustion reaction. So oxygen must be on the left for it to be a combustion reaction. Okay, so let's take a look. There are two types of combustion reactions that we can have. And the first one we're going to look at is combustion of an element, just an element on its own. And we're going to write that down, and then I'm going to get you to write a couple of examples down. Then I'm going to show you a couple of demonstrations. So the first type is the simplest type, combustion of an element. The second type we're going to talk about, and I just want to contrast this, is combustion of a fuel, all right? We know that there is all kinds of different fuels in this world. You guys use it, if you ever barbecued, you're using propane fuel. If you have natural gas in your house and you've got a gas stove, you're using methane, which is natural gas. This is what we burn here. In cars, gasoline is a fuel, all right? And we've seen, you've all seen combustion of a fuel. Burning wood is combustion of a fuel, all right? Yep. Combustion, yeah, I've got a spelling mistake. Yeah, that's supposed to be a 2 types of combustion. That's supposed to be a T. It's a spelling mistake. That's what, because I can't spell. Combustion. Good catch. But what I'm talking about right now is combustion of an element. It turns out that some elements can burn very readily. Magnesium burns like crazy. If you get magnesium hot enough, it will react with the oxygen and burn incredibly hot. Have you ever seen magnesium burn? Okay, I'm going to show you in a moment. So, when we are combusting an element, it's just the element plus oxygen to get that element's oxide. The general equation, note there is no element A, no such thing as element A. So this could be any of the elements that we want to burn. Some element, notice again, oxygen is on the left. Oxygen is on the left. And then you get A chemically combined with the oxygen to produce whatever the oxide is. Let's write down an example or two, and then I'm going to pause my recording, and I'll show you some. So, examples. We'll do those two first. We'll write them down, and then I will pause the recording, and then I'll show them to you. So, magnesium. Magnesium is used in all kinds of different places. They're used as auto parts. I believe there is a magnesium auto part factory in Strathroy. What's it called? Do you know what that's called? That company's called? Can't remember. Anyway. And magnesium is used in all kinds of different parts, airplane parts. It's a very light metal. It's fairly brittle. But it does burn, so it can be a little dangerous. So if If a piece of magnesium gets hot enough, it can burn. The second thing we're going to burn is carbon. Regular carbon is found in charcoal, like a charcoal briquette, but wood would contain a lot of carbon, and my lycopodium powder that I've burnt for you before also contains a lot of carbon. So I'm going to show you this again, but in a slightly different form. You'll notice that my two examples here are not necessarily balanced. Let's balance them for a moment and practice our balancing. Which one do you want to deal with first? What do you think? Which element do I want to deal with first in this guy? Which one do I want to deal with first? Yep. Okay, let's take a look. How many magnesiums on the left? And how many magnesiums on the right? That's good. That's good. Let's now deal with the oxygens. How many are on the left? 2. And how many are on the right? So what am I going to have to do with the coefficient in front of the magnesium oxide so that the O's are the same? What coefficient, what big number do I have to put in front? I have to put a 2. Oops. Let's get it working. 2. Now what's wrong? Yep. So I've got to go back and fix the other magnesium, correct? 2. Good job. That's balanced. It's good balancing. Let's look at the carbon one. Carbon's on the left. Right? Remember, there's a little 1 there. 1. Carbon's on the right. Again, when there's nothing, there's a little 1. So it's 1. How many oxygens on the left? Quinn? 2. How many oxygens on the right? That's a balanced reaction right there. That one works just the way it is, balanced. Okay, so right now let's pause this and let's take a look at some of these things. So I'm going to bring this up. Let's talk about now burning of a fuel. Actually, this is another element one, and we'll take a look at this as well. This is hydrogen gas. We can take hydrogen gas and burn it in oxygen. If you've ever seen the video of what is called the Hindenburg, does anybody know what the Hindenburg is? Yep. It's that Zeppelin that started on fire and then lots of flames. The Hindenburg actually had hydrogen in it, and so when it burnt, it created this explosive situation. I actually have a couple of videos here. I used to collect the hydrogen gas and put it in a balloon and explode it. I haven't done that for a few years because we have a student here that's allergic to latex. So I can't really explode a balloon because it'll send little tiny pieces of latex into the air. And if that student were nearby, they would be affected by the latex, right? So I haven't been able to do this for a few years, but that's okay. And I haven't been able to find non-latex balloons. But I've got a couple of videos here. And this is, again, a video of me, right? And that's what that reaction would look like. Don't mind that guy. So you can see there, it's quite energetic. All right, let's see it later on. Here is another explosion, but this time I've actually added some oxygen to it so that the reaction happens a little more energetically. All right, I don't know if you could tell there was a little more energy in that particular reaction, and that's because I added some oxygen to the mixture. That's what's in my tank right here. We'll be adding some oxygen to these mixtures. So that's also combustion of an element. So we can also burn gases like hydrogen. Okay, let's talk about combustion of fuels. For the most part, fuels that we burn are hydrocarbons. They contain hydrogen and carbon. Things like gasoline, natural gas, kerosene, propane, butane, found in lighters. That's a hydrocarbon. When these fuels burn, their products are carbon dioxide and water. Because when the hydrogen burns, it produces water, and when the carbon burns, it produces carbon dioxide. So the word equation for this particular one will always be a hydrocarbon, again, plus oxygen. It's on the left. It will always produce carbon dioxide, some water vapor, which means it'll be evaporated, and it'll produce lots of energy. Hydrocarbons produce lots of energy when they burn. Got to be safe. Okay, the general formula. In general, all combustions of fuels look like this. They have a certain hydrocarbon which contains some carbon and hydrogen. That's why it says X and Y. Same rule applies here. So some of our fuels have more carbon. Some of the fuels have more hydrogen. If I could get you guys to take your hats off too, please. That'd be nice. And in the end, again, it reacts with oxygen. Notice, again, it is on the left. And carbon dioxide and water are the products. So let's take a look at a couple of little videos on this, and then we will burn some hydrocarbons. The most of my demonstrations are the burning of hydrocarbons, all right? And then when it comes to the other two reactions, it's not quite as much. All right, so let's take a look at some examples. Write down that first example. And then we're not going to write down any of the other examples. We're just going to write down one example. So write down that first one. This particular example, the first one, involves a hydrocarbon that has the formula CH4. That is methane. That's what's called natural gas. That's what I was burning in the Bunsen burner, and in a moment we're going to make some bubbles of natural gas. Okay? And then we're going to burn them. This first example is not balanced. Let's try to balance this one as practice. The rest of my examples are balanced. What are we going to balance last? What do we balance last in this equation? There's one that's very obvious that we want to balance last because it won't affect anything else. What should we balance last? Pat? Oxygen. So let's do the carbons and the hydrogens first. How many carbons on the left? 1, right? How many carbons on the right? We're in good shape for carbon. Let's look at hydrogen. How many hydrogens on the left? 4. How many hydrogens on the right? 2. So what do I need to do with this coefficient? Make it a 2 so that it can multiply to get 4. Now we have to add up the oxygens, and I like to write that down underneath. Oxygens, right here. 1 times 2. There's 2 of them, right? How about the oxygens in the water? The oxygens in the water, 2 times 1 is 2. So how many oxygens in total do I have on the right? 4, right? Here, I have oxygens. There's only 2. I could put 1 times 2, but what should I put there to make 4? 2 times 2. 2. 2 times 2 is 4. Now it's balanced. We've got the right amount of oxygen for that combustion. Okay? The second one, this C2H2 is called acetylene. Where's acetylene used? Yep. Oxyacetylene torches. All right? This is the reaction that takes place in an oxyacetylene torch. When you get that exact right amount of oxygen and it burns nice and blue, you have these amounts happening at that time. When you don't have enough oxygen and it's burning yellow, it means you're choking off the oxygen and it's burning incompletely. We say it's incomplete combustion. But when you supply it with lots of oxygen, it burns nicely. We're going to find that that's true for all combustion reactions. If I cut off the oxygen, it doesn't burn very well. But if I give it the right amount of oxygen, it burns very well. This one here, this is a liquid fuel. This chemical here is called ethanol. Ethanol is produced by fermenting plants like corn, and then the ethanol is often put into things like gasoline in order to, have what we call a biofuel. I believe there's an ethanol plant in Chatham, and I think they're looking at putting an ethanol plant in Sarnia. I think in that area they're looking to put one. We're going to burn some ethanol in a jug, and I'm going to do what's called the rocket car. All right, we're going to see if we can use that ethanol to fuel it. I have a video of the rocket car right here. Now I do it differently than this one looks here. This is a milk jug tied to a string. Now that didn't work very well because it kind of choked for air. You can see how it burnt yellow instead of blue when it was slow. There you can see it burn all that yellow. It didn't get enough air. So what I do now is I add some oxygen to the mixture so it's got a good mixture of oxygen. Okay? So let's go back. So that's ethanol. These two reactions are propane. I don't do this demonstration anymore because I use methane instead. The one on the left, I don't give it enough oxygen. So here we've got propane with no oxygen. What I do is I make a bubble of it in a tray. And then I have a student come and burn that bubble that I've produced. So there I'm making the bubble. I'm using the propane cylinder there. And we burn it. And it burns yellow. Incomplete. But if, and I've got to find my propane with oxygen. Let's just click on it right there. Here, I've added oxygen to the bubble. And you can see there it's more energetic. Slow motion. That just sounds cool. That's just fun to do with that sound. Okay, so we'll do that in a moment as well. They're quite old. They're about 10 years old. That's before I had a red lab coat and I shaved my hair really, really low. Anyway, let's do some demonstrations. All right, so I'm going to pause my video again. I got to get to there and I got to pause it. Let's pause the video. And now I want to talk about a synthesis reaction. Yep. Yes, it is. I'm trying to make a movie as I go between blowing things up so you can watch the movie to the beginning of this. All right? Okay. Now you need to get my note out, and you need to put the phone flat. Okay, good. Okay. I'm recording this right now, so of course I've never heard anybody with a reaction. I've had, yeah, for all the movies that I do, you're on YouTube. Okay, stop. I have had an explosion be so loud that students and myself complained about, oh, my ears ringing, and then even the next day, oh, my ears are still ringing. So that's why I say for some that are going to be possibly loud, cover your ears up, all right, with your fingers. I've got one more reaction to show you other than the rocket car. They're already set up over there on those white pieces of paper. I'm going to show you that in a moment. And that one, I do need you to cover your ears. Because I did a test run with my grade 12s this morning. I forgot to get everybody to cover their ears, and bang, what the heck of a bang. Okay, so we do still need to learn things from our lesson today. We've done combustion. Combustion is when we have something react with oxygen, and oxygen is on the left. We have combustion of an element, like magnesium, to produce magnesium oxide, or we have combustion of fuels, like natural gas, and they produce carbon dioxide and water. Now we're talking about a different reaction. We're talking about a synthesis reaction, all right? And synthesis means to make something. It means to make something new. So it means that we are combining molecules or atoms to form a larger molecule or atom. This is the general formula. So we're going to have elements in place of this. The way you can determine if it's a synthesis reaction, you will always have two things on the left and one thing on the right. So please write that down underneath that general reaction. You will have two things, two reactant molecules on the left, and you'll have one product on the right. Okay? So a synthesis reaction means to make something new, two becomes one. All right? Yep.
So would it be like combining two gases?
You could. It could happen. Yep. But typically it's two elements coming together to react in some way. But it could be that way. Yep. Okay. So the example here that I have to begin with is aluminum and liquid bromine. So solid aluminum and liquid bromine. Again, for our examples, I like to have you guys balance one of them at least. So let's balance this one as well when you write it down, and then we'll take a look at that reaction online. I cannot do this reaction in the classroom because the bromine evaporates, it becomes bromine vapor, and that's not necessarily a good thing to have a lot of in the air. Okay? So let's take a look at this. Notice in this balancing situation, I have a 2 and 3. Look at the bromine. Remember yesterday when we talked about the 2 and 3 scenario? And students usually go, what do we do? How do I fix the 2 and 3? Eric? No, you know what? You can do a 1.5. That cheat does work. But I was thinking about the other way to fix it, but you can do a 1.5. It will work. But what was the other thing that I did? Yep. Switch them, multiply the one that has the 2 by 3, and the one that has the 3, what do I multiply it by? 2. So if I switch them, and I go 3 and 2, notice my bromines now are 6. I've got that taken care of. Now I just have to deal with the aluminum, and I got to multiply it by 2. Okay? So that's that 2, 3. But you know what? A half would have worked, because the aluminums were balanced, and if I put 1.5 in front of the bromine, that would have worked as well. There's two ways of doing that one. Let's look at this video. Now, I just have a link to it right here. That's the easiest way to do it. This is not me. This is one I found online. So there they're putting little bits of aluminum just into some liquid bromine. Remember, bromine's a liquid. No heat is required for this reaction. It spontaneously reacts. There you can see some white powder or smoke coming out. That's the aluminum bromide. Here you can see the liquid droplets of the bromine falling back into the beaker as heat is produced. So this reaction happens spontaneously. It gives off energy. And in the end, the white smoke and the white powder on the rim is the aluminum bromide. Okay. Don't write this one down. We've got one example written down. We're good. This is zinc and sulfur. I've shown you zinc and sulfur in the other room, the other laboratory, when we were talking about chemical properties. This is one of my videos, again, about 10 years old. And I actually did, nice. That was my other reaction. It already went off. It already went off. That is awesome. Okay, let's take a look at this one here for a second. And I'll tell you what happened there. Okay, let's stop this. That is good stuff. That's okay. All right. Okay, everybody relax. Everybody relax. What you just heard there and what just happened was a decomposition reaction. That's the next type of reaction that I'm going to talk about. That was a chemical called nitrogen triiodide. It is what is called a contact explosive. Normally you have to hit it with something to get it to explode. That, for some reason, spontaneously exploded. I don't know whether it was the other explosions in the room that resulted in that thing going off. I do have one more on the left. So you'll notice on the left, there's one more ready to go. I'm hoping to show you that in a moment, as opposed to it being spontaneous. Let's talk about what a decomposition reaction is, and then we'll go over there. All right, let's go ahead. We're jumping ahead here. Decomposition reactions. Please write this down. So some of you who already wrote other examples down, that's fine. All right. If you've wrote ahead, what I'm looking at now is, and if you didn't write ahead, don't worry. We've got an example, one becoming two. I think I've distracted you from what we want to learn here by all of these explosions. We might have to do a little review tomorrow at the beginning of class. Remember, synthesis was two turning into one, right? Two turning into one. Decomposition is the opposite of a synthesis. One breaking down into two. Question? No, it would be a synthesis. There's sulfur in there, there's carbon in there. I don't know what our other things are, but those are combining to make a gaseous product. No, that strike is to produce a little bit of heat to initiate the synthesis. So it's not the strike that makes that a decomposition. Decomposition can happen in many ways. Just that particular chemical is one that needs a hit to initiate it. So gunpowder would be a synthesis. It's burning and synthesizing, putting elements together. Yep. Combustion and synthesis are very similar. Combustion, you're combining oxygen with a substance to make the products. But there's also other elements coming together with oxygen in a synthesis way. Combustion is a type of synthesis because we're making those new products by combining it with oxygen. Okay? All right? That's a good question. Notice in this one, decomposition, it's breaking down. Look at how many things do I have on the left? How many compounds or how many items are on the left? There's one. And notice what happens on the right. It breaks down into two. So when a single thing breaks down into two, it's decomposing. It's breaking apart into simpler things. So a synthesis is when two things combine to become one. You synthesize something new. And decomposition is when one thing breaks down into two. Okay? One thing breaks down into two. And I've got a bunch of examples of it, but who's kidding who? Let's go right to the example I want to show. Write down example number 2, because that's exactly what happened over there. And then I'm going to show you that last demonstration. I'll show you what it looks like. You can write, if you wrote down example number 1, there's nothing wrong with it. Just notice in all of them, one thing, even though it has a coefficient of 2, it's one object becoming two other objects. That's how you identify it. Now, if you're just writing example number 2, that's great. That's awesome. Notice it's not balanced. So let's balance it as well. And again, I'm seeing a 2-3 scenario with iodine. By the way, this is a capital I. You can put like the tops on it if you'd like. It's an iodine. So this chemical is called nitrogen triiodide because it's a molecule, and it's going to decompose into N2, a colorless gas, and I2, a purple gas. Did you notice that? Yeah. Yep. A purple gas. Let's balance it. Look at 3 and 2. So what am I going to put in front of this guy? As soon as I have 3 and 2, I'm doing the switch, right? So I'm going to put a 2, and what am I going to put in front of this guy? The 3, because 3 times 2 is 6. 3 times 2 is 6. How many N's do I now have here? 2. And how many here? 2. It's balanced. Let's watch the video that I found online. I did not make this video, but this one entertains me because it's being done in front of a class, and they react. Oh, first I got to watch an advertisement. Skip. I love the reaction of the classroom. Had 2. That's why this guy has 5. He's going to detonate the bottom one, and this shock wave from the bottom one is going to detonate all the rest. And you can see students in the reflection of the fume hood. He uses a feather. I love the screaming. Like it's almost like they're crying. It's almost like someone died doing that. That was exciting. So let's take a look. Let's take a look at this last one here. So I am gonna, and you know what? I do have some examples that I want to go through with you, but I'll do that tomorrow. So you can close up for today. We'll start tomorrow by doing the examples. And let me detonate my last nitrogen triiodide.